So what we'll be seeing today, just recap of what we have seen previously. We use linear architecture to do image classification, and it gives us a very good performance in some ways, which are these. Remember, this is the first model which we had, and it gives us called Passion MNIST version 0. It gives us model accuracy 83, and this is a loss. And we improve this model because this model is just linear model without non-linearity. And now we introduce linearity, remember, and our model gives us this, which we call more Passion model version 1. And after we introduce linearity, we saw that even the model accuracy dropped, meaning that introducing linearity doesn't help. That's what we discussed in the whole thing at the top, which we are not going back. But today, what we are going to see, like, how can we have a better performance model that can do better for image classification? That's what we're gonna do. What can we do for image classification to have a better performing model? So this brings a question that instead for us to use linear model or whatsoever, in machine learning or deep learning in general, we have classified architecture that are useful for any kind of data you have. Because you can see we use linear model. So linear model here, it means we use linear model previously. Remember, we can use it for text, we can use it for image, we can use it for audio. They are just linear. But in deep learning, we have specialized neural network architecture that can be used to solve problems. So our problem we are working on, if you remember, we are working on image classification. Now, deep learning brings a specialized architecture called CNN. Yes, it's called CNN. CNN, all right? CNN, right? Yeah, convolutional neural network is specialized architecture for image classification. Now, since I said we have different kind of neural architecture, this bring us different kind of architecture we have. So you can see in neural network, if you remember our machine learning book club, we discussed about perceptron. Then perceptron move forward, we have feed forward neural network. So what we saw here is just basically feed forward, but deep feed forward, because we have many layers, right? So what we saw is deep feed forward. So you can see we have feed forward where it basically have the input layer, we have the hidden layer, then we have output layer. This is called feed forward. What we have also what we call deep feed forward, where we have many layers, right? And now we can see we have another type of network, which is called recurrent neural network, RNN. What interesting thing here you can see is that when an input comes from here to the network, the output of the network go back into the network. You can see the output go back, something like that. So we have LSTM, GRU, autoencoder, denouncing whatsoever. You can see many kind of network, deep convolutional neural network, many different kind of generative neural network, support vector. So yeah, so what I'm trying to say here in essence is that what we did previously, we just try to use deep feed forward network just to do the calculation. And it turns out to give us, but we can do better when we employ CNN. So let's go over to see some of these architectures and what they are used for. So these architectures, basically, if we look at the first one, feed forward neural network, these are the most basic type of deep learning architecture. They are the most basic deep learning architecture. So for example, it is you and that you want to say like, hey, I want to basically to, buy a car to drive me from here to somewhere else. So you can buy different kind of cars, right? You can buy Peugeot, you can buy Mercedes Benz, you can buy, Honda. So that's also why if you want to do deep learning, you have different architecture that, so if you want to find a rugged car, right? Maybe you want that, you can buy for Peugeot, right? Peugeot. If you want to buy luxury car that's speed, you can buy, Benz, right? So what I'm trying to say, like, is like different kind of field requires different kind of architecture here to work off. So this we have feed forward neural network. They are the most basic of deep learning, and what they are basically have, they consist of connector layer, and for example here we have input layers. Now you pass it to the hidden layers, then you have output layers. We have seen this one before, right? So this is called feed forward. The condition is that feed forward must have at least input, one hidden layer, and the output. That is, feed forward. So this is basic feed forward neural network. But also we have convolutional neural network. So what are convolutional neural networks? So these are networks designed to process and do excellent work on image, and they consist of many layers called convolutional layers and fully layers. So you can see this is feed forward. So feed forward, you just have an input layers, pass it to what we call hidden layers, and but now in convolutional neural network, we have what we call a layer. So here it's just called hidden layer. But in convolutional neural network called CNN, we have what we call convolutional layer, we have what we call fully layer. Then finally, after we have this, then we have what we call flattening, which will flatten your stuff and predict the output layer. That is basically, the convolutional neural network. So you can see it's different from, feed-forward neural network. Then we have also what we call recurrent neural network. So this convolutional neural network, they are used mostly in images. So if you have images, if you want to, for example, build a deep learning network that detect image, whether it is a cat, whether it is a dog, then don't use feed-forward neural network. The architecture that is suitable for that is CNN architecture. But what about if I want to not just this, detect image, but I want to translate from Hausa to English, or I want to do, some kind of sequence stuff, like maybe voice recognition. You don't use CNN in this way. We have specialized architecture for, dealing with this kind of stuff. That architecture is called recurrent neural network. So this is recurrent neural network. So you can see, this is recurrent neural network, and basically this architecture, you can see it has input layer, then we have hidden layers, then we have output layers. So what is happening here is that the recurrent neural network, the output of this layer, you can see, you can see like it's become the input in some ways. So what is happening here in the recurrent neural network is that, let me just give you an example. So if you want to do translation for the word, you want to translate this one. I love this house, right? So if you want to translate it, if you translate this one here, this word that you want to translate must have access to the previous, you must know what you have translated before. That means that you don't translate this one first, this one, and you return it, this one you translate, they must have some kind of memory. If I translate this, I must know what I translate before, some kind of memory. So this is what we call recurrent neural network. So RNN have a memory where remember information. We'll discuss about this stuff in detail, but just I'm introducing us to different kind of architectures we have in deep learning. So that's different recurrent. So you can see RNN can be used for machine translation, time speed recognition, speech synthesis, many stuff. This is where RNN is used. But also we have what is called another architecture, deep neural network architecture called generative adversarial network, which is called GAN. So what this is, so GAN is developed by what we call Encoder, who wrote a book on deep learning. I know if you are using deep learning, you must know the book for Encoder, which is deep learning. So he developed this, and the architecture GAN, it has two different kind of networks. We have what we call generator, and we have what we call discriminator. So a generator that generates, so for example, now if you want to generate a new image, fake image of something, so we can use what we call GANs. So how does GAN work? So you have a real image of Buhari, and I want to produce a fake image of Buhari. Now, what I can do is that I start with some random numbers, with a network called generator. This generator will try to generate image based on the real image of Buhari. Now it produce the sample. So here from real image, we have the sample. Then we have another network, discriminator. So this discriminator will say, okay, now this fake image that this generator generates, does it look like this? Does it look like the real one? If it is not look like the real one, if it doesn't look like the real one, then it will feed. If the loss is high, it will feed forward again. To update the generator, to update the weight and some whatever. So this is what we call GAN. So it has two architect, network, generator, and discriminator. Generator generate new stuff, but discriminator tries to make sure that try to see whether the fake stuff. What we generate is looking like the real one. This is just the high level, but there are a lot of theory behind that. But just I'm here introducing at high level. We will go into the details of this, but just for you to know different kind of neural network. So what I'm saying here is that when you want to do deep learning, there are many kind of architectures you want to use. So this is feed forward. This is convolutional network, neural network. If you want to deal with images, this is CRNN. If you want to work for machine translation, if you want to work for maybe sentiment analysis, anything that deal with text, you know what I mean? Sequence. So for example, you can even use this for time series. So RNN can be used for time series because time series is also sequence. So anything that is sequence, we can use RNN. But what GAN? So GAN can be used in a situation whereby you want to reproduce something. For example, here we can see you can use GAN to generate realistic image of faces, generate new image of text description, generate new video, improve quality, creating 3D. All this stuff you can use with GAN. The next one is transformer architecture. So this is the most exciting stuff now in the real world. Even the GPT you are seeing, they are based on transformer. I believe we all know what is Chat GPT, right? So Chat GPT is built based on this architecture called transformer architecture. So transformer architecture, it involves what we call encoder and decoder. And for example, when you impasse something here, just a text here in English, you pass it to encoder, and the decoder will output Chinese. So we have some hidden sets, some stuff here inside details I will show a bit. And these details, they are the one that translate from English to Chinese. So this is called a transformer. So you can see a transformer is different from GAN. You can see transformer is different from RNN. You can see transformer is different. So each and everything you want to do, you can actually use different kind of architecture. And so this, what you see here, this one, the transformer, this is the detail of it. So it involves what we call, each transformer, it has what we call multi-head attention and feed forward. So you can see feed forward at the last one. So it consists of multiple decoder. We can see this is the decoder with multi-head attention. So, and the last one is always feed forward. Yeah, so this, you can see this is the encoder. This is the we can see decoder. Okay, this is the decoder, this is encoder, right? So this is a high level of what this inside here. If you don't understand this architecture, don't be confused, because we are not saying you to understand the detail of this architecture, which we'll do later, but just here to tell you we have different kind of architecture, just to tell you. So example of transformer based models, what we can see from transformer, this is what we are using instead of the art NLP and even vision, even computer vision. You can see we have what we call BAT. We have BAT, we have GPT, we have Robata, we have T5, XLN, Alvata, Megabat. All these architectures, they are based on what we call transformer-based architecture. And they are the one that now, they are doing the state-of-the-art, stuff, whether in computer vision, even time series now, we have transformer-based models. Of course, now, as you all know, Chat GPT now is ruling everything, and it's based on transformer-based models. Yes. And now finally, we have what we call autoencoder as well architecture. But yeah, so this is just a brief recap of, different kind of architecture that I made mention. We have a general overview. So the reason why I, discuss this is just to tell you that it is not enough when you want to do deep learning to just use the feed-forward network. No, just determine first what kind of architecture, what kind of problem you have at hand. Is it image? Okay, it's image I'm trying to do. Oh, okay, let me go with CNN. Oh no, I'm trying to do with text, machine translation. Oh, let me go with RNN. No, I'm trying to use, some kind of adversarial network. No, let me use GANs. But oh no, I want to have something that can solve every problem. Transformer, that is transformer. Is domain specific. It doesn't care whether you are using image, whether you are using text, whether you are using multi-time series. Transformer is all you need. That's the title of one paper from Google. Even that's the paper that actually started to bring this this kind of improvement we have now in deep learning is based on. So that's why it is called transformer. Is only attention is all you needed in the paper of attention. You can see something attention. Okay, so let's go back to our problem code. We continue coding our classification. So based on what we discussed, any question? Any question? Okay, so let's continue. It means we are done. So let's go back to use CNN architecture now to try to solve our problem we have for the classification. So let's go in detail to see CNN. So CNN. So what is CNN? So CNN, as we said, it does have several stuff. It has what we call convolutional layer, Fully layer, convolutional layer, Fully layer, and finally, then you need to flatten what is at the end and to do classification. You can see that in the input of our image. So we already said that the CNN, it consists of convolutional layers. So these are the convolutional layer. You can see that. The second one is the Fully layer. So convolutional layer, they try to capture some of the important information from the input image, and now they and the Fully layer, they reduce the image or convolution layer. So we're gonna look at this different architectures here. Okay, I'll come back. So this is what happened now. If you have a simple image and you want to do classification, what we need to take this image, change it into tensor, right? And now pass this tensor of image to convolutional layer, pass the convolutional layer to ReLU layer. We all know ReLU layer. What is ReLU layer? ReLU layer, we all know it is, non, who can tell us what is ReLU layer?
Rectifier linear unit.
Yes, okay, rectifier linear unit. It is non-linear activation function, right? Then we have Fully layer. So this is what is happening in CNN simply. But here you can see we have one block, right? It must pass. This is one block, convolution, ReLU, Fully layer. This is one block of CNN. But you can have, deep CNN. So you can see simple CNN, only one block. So deep CNN, you have convolutional layer, ReLU, Fully layer. That is one block. Then you have another block, convolution layer, deep ReLU, another block. So why do we need block? So the more deep you have, the more deeper you have. That's what we have. Deep learning, meaning it must have, deep layers. You have different layers. So the more layer you have in deep learning, the more you'll be able to extract more information. So if, for example, you now see the GPT example, GPT is using many layers of over, 175 billion parameters with many layers. So the more layers you have in deep learning, the more you will be able to extract meaningful information from your architecture. So yeah, so that's what we mean. So also CNN are sometimes called linear covenant. Yeah, so they are also called covenant, CNN architecture, a convolutional neural network. And let's look at some example of what is happening in CNN here. Let me show this example. All right. You can see my browser, right? Can you see my browser?
Yes.
Okay, so let's look at what is really pictorial, what is happening in CNN. So you can see this is an image. I select this image, right, for coffee. So I have read. You can see this because okay, let me choose another one. All right, okay, this one is okay. Okay, let me choose this one. Okay, what about this image? Okay, some comment. No, what is this? Is it dog or what? Anyway, so we can see if we have this image, you can see this, we have channel, red, green, blue, different channel for the image because it's colored image, because the input we have is 3. You can see the input is 3, which means it's a 3 channel, right? We have red channel, green, this is our input. So the input here, we have all this input. They are, remember we have channel, then height and width. Remember all this we have. So this is our channel. Now, if you look at this one here, if this, you can see convolution. Can you see convolution? So this is what I was talking about. If you remember, this is convolutional layer. You have convolutional layer. Now, then you have ReLU. You can see ReLU. This is ReLU. You can see ReLU. Then, then you have convolution one again. And you have what again?
I cannot see your browser.
Oh, okay. You cannot see my browser?
Yeah, I can see it.
Okay. Oh, sorry. I was opening another browser. So this image, okay. Okay. So can we see the image now?
Yes, yes.
So you can see we have image, and the image input is we have channel 3, meaning that it's colored image, not grayscale, because we have 3. So you can see red, green, blue. Now, if we look at this image, remember here I said we pass our image to convolutional layer, the ReLU, then fully layer, right? So this is what is happening. Can you see the convolution layer of one? So you can see something is coming, copying from the image, or something is happening. Then we have bias added to something. Can you see? So this is learn some stuff from this image. Can you see it's taking, can you see some opening here? Like it's trying to detect the image here. So it's trying to this canal, we have what we call canal, is trying to imitate, to detect some patterns from the image. That is what is happening. If we go to this one, ReLU, you can see now we have ReLU, and now the ReLU, you can see we already know the ReLU can take the maximum of stuff. So the ReLU will act on this, on this output of the convolution. Now we pass the output of the ReLU to come here. You can see intermediate here. We can see it's still learning. We have the ReLU one, and now lastly we have the maxful. We can see the maxful. So we'll discuss about all of this in detail, but just trying to show you. So what this is all about. So here we are doing image classification. This is just example. And now let's see this image, this one. So you can see we have many blocks. So from here to here, it's one block, because our convolution, we have ReLU convolution. Then last one is max ReLU, maxful layer. So this is one block. Then we have another one, convolutional 2, ReLU 2, because here you can see conv 1, ReLU 1 means one block, the first block. Then the second block, we can see we have many other things. And now we can see the output here, because how many output do I have here? Maybe I have 10 output. So you can see, because here I select the coffee, here I select the coffee. Now you can see espresso. You can see it tells me it's espresso, the output, right? All other thing, live board. So let's look at this. This is a live board. You can see the answer is no live board. What about if the image I input is a live board? Okay, let me select the first one. This is the live board, right? So live board. So the convolution here, for example, is going on, and in one class, right? Can you see that it's a live board? If I select the something here, which is car, I think, car, can you see the class is school bus? Can you see that? So what I'm trying to say here, this is just like classic, CNN explainer that shows you how this architecture is arranged. So we have convolution, and we have maxful convolution, ReLU convolution, and maxful. So we will discuss the detail of what is maxful, what is ReLU, what is convolution in a bit. But just to show you, what is happening inside. Any question? Okay, so let's go back to our. Yep. So you can see this is what I was saying. If you want to typically use, CNN architecture, what we basically do is we take our image, convert it to tensor, now pass the tensor into convolutional layer, ReLU, then full layer, which is basically these things can be combined in different ways, as they say, meaning you can have basically convolutional layer, you have ReLU, then you can have another convolutional layer, a ReLU without the full layer. You can see here I have three things arranged: convolutional layer, ReLU, full layer, right? Three things. But if you look at this one here, convolutional layer, can you see one convolutional layer? Then I have ReLU, right? I don't have the maxful. I just have two here. Then I have another convolutional ReLU and maxful. Can you see? So that's why we are saying this can be combined in many different ways, but we are not here to explain those. But this is deep one. You can concatenate them as well. Okay, so there are also many different kind of architectures. We have, as I told us, like here, that in Transformer, we have different kind of architecture, such as BART, GPT, Robata, P5, Albata, Megabata. We also have different kind of architecture in CNN. For example, we have LeanNet, AlexNet, BGG, Inception, ResNet, DenseNet. they have different architecture. Now, if you want to use image classification, what you need to do is just come and select one. If you want to train, maybe image classification for dog in your country, in your project, select one of the architecture and use it, or read which architecture is best, because some architectures are better than one, because it's time, something is time specific, because if an architecture is built in 2001, then the architecture now in this today may have better performance. You can see this one is 1998. You can see this one in 2022, 2014, 2015, testnet in 2016. So what I'm trying to say is that you can have different architecture, and they have different performance. If we go to PyTorch, let me show us PyTorch. So if we go to PyTorch, yeah, so everything that is based on touch vision in computer vision is under models, AR models. So touch vision that model. So look at the classification model we have. If you want to classify image in using PyTorch, just come and select one of these models. You don't need to create it from scratch. As I showed you here, this is an example of a neural network here, which is basically it has this. So there are different ways to do this arrangement. That's why we have different architecture. So, but here, classification model here you can see we have AlexNet, which I showed. So if you look at the AlexNet here, look at the paper, you can see the paper, AlexNet paper. You can see if we open it. Okay. Yeah, so this is AlexNet paper. You can see that. So you can see this is the architecture. You can see this is how it is arranged, everything. Can you see that? So the good thing is you don't need to create it from scratch. PyTorch already have the architecture. For example, BGD is also another architecture. You can see deep convolutional neural network. If you go here, very deep convolutional neural network, you can see the architecture here. Oh, okay, they don't have PK. Okay, they don't have image here for us to see. So in any way, so that's what I'm trying to tell you. We have different kind of let's see GoogleNet. Okay, GoogleNet. Oh, this is Inception. So Inception is also another architecture for image classification. Maybe this is the GoogleNet. Can you see that? Wow. Can you see different? Can you see GoogleNet network with all the bells and whistles? So you can see the MPA convolution, Maxwell. You can see they add another convolution. Everything. So don't bother about all this. Structure. If you want to use any of this architecture, PyTorch has the key implementation for everything. You can see if you want to use ResNet, if you want to use AlexNet, if you want to use BG system, if you want to use Inception, can you see Inception version 3? If you want to use DesNet, you call models dot, that is if you want to. So you import this one, import touch vision models as models. So you now import all the models. So if I want to use ResNet, all I need is say model.resnet 18. If I want to use AlexNet, it's modelnet.AlexNet. So you see all of these models. So they are available for you. You don't need to create everything from scratch. Yeah, so we'll see, we will now take one of these model to implement how we can use maybe BGG system, and to see how you can design a deep learning model for classification using image. Right, any question? Any question?
No
Okay.
question for now.
Okay, so let's take BG16. So from here, we saw that BG16, can you see we have something called BG16? It's a model. So we take it and build a model. All right, so let's look at it. So partial MNIST version 2. Remember, we did have partial MNIST version 0. We have partial MNIST version 0 is the one that we did linear network, linear feed forward. Partial MNIST version 1 is the one that we had non-linearity. It doesn't give us better performance. But now we are moving to create another model called partial MNIST partial model version 2, right? So let's look at how. So here, what we're gonna do is we're gonna basically replicate this model, this CNN. We can see because this one is good in some ways. So when we select this one, you can see it gives us espresso, which is coffee. It was able to classify, given 10 images, classify which one is correct. So we're gonna replicate this architecture in our model. So now we create a class. We already know how we create class, and we know that each class we create must subset the NN model, right? We already know this. If you are joining us today, we are already familiar with some of these steps, so you can see us maybe moving faster. But if you want to join us from today, you can watch our YouTube channel so that you can get up to speed with what we discussed. So for any class we want to train, it must subclass NN module. And now here we know is this, and now here we define a function and what we expect for the model: input shape, hidden unit, output shape. We already know that a model that we want to define must have the input shape, hidden shape, and output shape. Yeah, so this is this, and we call NN sequential, right? NN sequential. And how does this looks like? So this looks like given input, convolutional neural network, the ReLU, right? So let's look at it. So we call it self convolution block 1 because I want to build block 1 here. This block 1, NN sequential. That is how we are building our neural network. NN sequential, NN.conv2D. NN.conv2D. Remember previously, what are we using previously here? Are we saying NN.conv2D? Who can remember us? Remind us, what are we using here in the previous model that we built? What are we using? What are we using here? Who can remind us?
N.linear.
Yes, linear. Yes, exactly. Linear. Let's go back. Yes. Can you see linear? Can you see we are using linear? Why are we using linear? Who can tell us why are we using linear previously? Why are we using linear previously?
This is feed forward.
Yes, exactly. Exactly. We are using feed forward previously now, but now we are not using feed forward. We are using convolutional neural network, and we have conv2D. So who can tell us why are we using conv2D here? Why don't we use 1D or 3D? What is the meaning of 2D?
It's two-dimensional.
Okay, so we have conv2D here applied to a 2D convolution over an input singular. So we have our image is 2D. If you have like text, maybe it's conv1D. If you have like video, if it is 3D, some stuff. So because we are using 2-dimension stuff, that's why here we have this. Yep. So let me show something. And then where is touch? Yes. Yes. So can we see we have something called convolutional layers? Previously we were using linear layers. If we come to use RNN, can you see we have recurrent layers? What I already discussed here. You can see we have transformer, we have adversarial network, we have RNN. So if you look at them here, we have recurrent layers, we have transformer layers, we have linear layers, but here we are using convolutional layer. So if you look at convolutional layer, you can see we have conv1D, apply 1D convolution over conv2D, apply 2D, conv3D, apply 3D. So our image is just basically 2D, right? So that's why we are using that thing 2D. All right, so we have conv2D. We have input channels. Remember, this is our input shape, right? Our output shape. Output channel is hidden unit. Remember, this is what we have hidden unit, right? And then if you remember in our linear layer, we only have input shape and output shape. If you go back here, right? In our linear layer, we have only input shape and hidden unit, right? input and output. That's what we have in linear layer. But in convolutional neural network, we have many other things which are hyperparameter that we need to introduce here. We have something called kernel size. We have what you call pride. We have something called padding. All these things are hyperparameter. All these things are called hyperparameters. Okay, what are examples of 2D image? So 2D image, just like an image you can see in your hand, like in your computer, they are all 2D, they're in 2D shape. So image that we have, a normal image is in 2D shape, right? So these are called hyperparameters for convolutional neural network architecture. So you can see here we have input with the output. Our input is input shape. We have hidden shape, but we now have what we call kernel, and we have what we call stride. We have what we call padding. Let's go back over to our CNN explainer here. Now, if we go back to our CNN explainer here, if I click here, not this one. Okay. Oh. Okay. I want to add some. Okay. We have what we call some hyperparameters in convolutional neural network, which we have what we call kernel size, stride, and padding. So what are these kernel? What are these stride? What are all these? So let me go over maybe here. So in deep neural network, in convolutional layer, we have what you call, I think here there's example here. Oh yeah, wow. Okay. So let me go over here to the example. Okay. So if we look at this image, look at this image is trying to capture some, future from the image here. But look at how it is going. Now, if we look at how it is going, can you see, like, let me play. Can you see it's going maybe one at a time, one at a time, one at a time, So this is what we call, we have what you call here. Okay, let me give up. Yeah, will be a good example. So this is canal size. We have what we call, for example, let me change this one. So if I leave this canal to be 1, let's see what will happen. Right. Oh, okay. So can you see like what I have here, canal size is 2. Now, can you see is okay, let me use canal size is 3. Okay. Anyway, I thought this one is like moving itself. All right, so let me just show us from here. I thought this one. Let me see. Yeah, again. It's still going, it's going. So if I change 2 here, not 2. Okay, let me move on. I don't know why it's not working. Anyway, let me move on to our explanation. So what you should know is that in convolutional neural network, we have what we call canal size, we have what we call stride, we have padding. All these ones are hyperparameter. We know in machine learning or deep learning, hyperparameters, these are some of the things that we can change so that by our hand, these are numbers that we can change by our hand to see whether how the model behaves. I think I will come back and explain all these hyperparameters because they are really important. But oh yeah, so what I'm trying to say here, you can see I have this, then I have ReLU. So as I said, we will replicate this architecture, this one, yeah, this architecture. So you can see we have convolutional linear network, then we have ReLU. Convolutional linear network, we have ReLU. So this is what we have, convolutional. We can see that. Then we have ReLU. We call NL del ReLU, right? Then what do I have next? Convolutional linear network, ReLU and Maxwell. So I have another one. So I have convolutional linear network, ReLU, and Maxwell. So all this one is what we call the first block of convolutional neural network. This is called a first block. That is why here I say conv1, ReLU1, conv1, ReLU1. Then you can have another block, which means that you can even train your classifier with convolutional neural network with only one block. But the more deeper you go, the deep neural network, the more deeper you go, the more it will be able to extract more information. So you can see here I have the first block here, which is this. So I define myself convolutional block 1. I use NN sequential. So inside the NN sequential, I have I have my convolutional neural network. I have my ReLU, and now another convolutional neural network. I have my ReLU. Then lastly, I have what is called Maxwell. So this is a Maxwell. We can see that Maxwell. Then another one here, I have convolutional neural network ReLU, which is this. I specify convolutional neural network. We can see that. Sub the convolutional neural network 2. We have sequential. This is it. We have ReLU, which is it. We have another one. We have ReLU. Then we have Maxwell at the end, right? I finished this one. Can you see I finished the second loop? And then lastly, we have what we call classifier layer. So we can see the output here. It will give us 13 by 13, the output here, the last one here. So we need to, put a classifier layer at the end here to give us a classification of the last thing when you do a prediction. So everything from here to here is you are training the model to learn from top. But at the end, you must flatten the matrix that will be output here. You must flatten it to give you the classification layer. So let me show us here. This is the example. This is the example. Convolutional. Can we see this image? Or let me change. Okay, maybe can we see it now? Can we see the image?
Yeah, we can see.
Okay, so if you have an image here, what we know, we already say convolution, fully layer, convolution, fully layer, but there is ReLU here, remember? But finally, after you finish all this one, this step is what we call future learning. If you are using CNN architecture, from convolution to the last is what we call future learning. After you finish your future, you need to take the last matrix and flatten it. Can you see we flatten it? When you flatten it, then you pass to fully connected layer. Remember the fully connected layer we did previously? Fully connected, you just call it, and now you do the classification. Because here we want to classify three things, whether this is computer, OCA, or doc. So because it has highest potential 0.83, we have computer. That is the essence. So what I'm trying to show you here is that when you are using convolutional neural network, you need to train the model here. All these steps, they are called future learning. Now, after you finish everything, then you need to flatten your final matrix here to flatten it to be a single matrix like this. Now you call fully connected layer because fully connected layer, it can do classification, right? So you call it here. That's what I want to show us here as well. Let me go back to the theme, GitHub. Okay, so that's what I want to show us here. If you remember, this is the CNN architecture. We can see CNN, convolutional layer, Maxwellian, convolutional Maxwellian. And finally, you need to flatten the last Maxwellian matrix to flatten it. Then you need to call fully connected layer and you make your prediction finally. So this is what we want to show here. So if you look at them here, our matrix here, after we finish everything, now create a classifier. Then I create, can you see I call class NN sequential again? and I flatten. Remember, this is what we did last week and yesterday. I flatten. So this flatten will it will create something like this, the output here. And now after it flattened that one, then we need to create a linear layer that will do classification. Then what is the input feature? And now the output feature, we have output shapes. So what do we mean by output shape? How many classes do we have? 10. So that's the output shape, length of the how many classes you have. And now here is the input feature, which is the what we have hidden, which is 7 by 7. I will show us how we got this 7 by 7. Now, finally, we finish, defining our architecture here. You can see that. Then we can just call a forward method. So we can see here we have a forward method. So for those of us that join us here, they are from REO Data Science Fellowship. You may not understand, I think, what we are doing. We have been doing this for over a month. So it's just something we are doing in PyTorch. But for also REO Data Science, we'll go through PyTorch as well. But if you already have background of deep learning and PyTorch, you can catch up. But you may be confused, but yeah, you are fine to stay. Yeah, but just to let you know that we have been doing this. So yeah, okay. So here we finished everything here, defining our architecture. Now we call our forward method. So this is our forward method. Now what the first block we have, div block, we can see that we call NN in NN sequential, which is this first block. We can see that I pass X, which is the input we're gonna have, the image, our image. Can we see X? I call self complete here. And the output of the first layer, first block, I pass it to the second block. Can we come to X, which is this second block? Well, second block, yes, this is second block. We can see that, right? Which is this, and the output of second block, we pass it to our linear layer, which will do classification, which is this sub.classifier. We call it classifier. Can we see that? And this sub-classifier, what we call first, we call the flatten, stuff. Then we call the linear layer to do the classification. Then we call this, and finally here, we finish building our this model, fashion MNIST version 2 model. Then finally, we can call, we create an object model 2 fashion MNIST version 2, input shape 1. So what is input shape? You remember the image we are working on has the channel 1, which is gray image. So you put 1. If you are working on image that is has 3 channels, that is colored, you put the input shape, you put it 3. But we are working on gray image, just put 1. That is what we do in computer vision. So here, what we have, input shape, remember, you should put 1 because we are using gray image. So we create an object called model 2, which is input shape is 1. Then the model, we put input shape, then hidden unit, how many hidden unit do we want? We said, okay, use hidden unit 10. Then lastly, what will be the input of the image? Output shape. How many shape are we classifying in our problem? Remember, in our problem, we are classifying how many classes? 10 classes, length of the classes, 10 images. So this will be 10. And now here we'll push it to devices, whether you are using GPU or something like that. So we push it. So this is our model we build now based on CNN architecture. And yes, so this is our biggest model we have seen which is yep. So what do we do basically in machine learning is just to get some architecture, go and copy the structure and the architecture, because you don't need to design new architecture. Yeah. All right, any question? Okay, so we have seen now that in what we've seen, this is the input layer. We have conv2D layers. We have ReLU here. We have, activation layer. We have pooling layers, output layers, lastly. But let's go now into details discussing about what is this kernel size? What is this stride? What is this padding? What is this maskful 2D? What are they? Let's go now into detail and see what they are doing. So hyperparameters, we know in our deep learning, we have in channels, output channels, kernel size, stride, and padding. So what do they do? Input channel, define the number of input channel of the input data, the input channel. So what the input channel, because our input channel here, we know basically we are using the gray image. So input channel shape is 1. So that's what this means, right? 1 for grayscale, we can see, and 3 for RGB. So always, if you are using computer vision, the input channel will always be 1 or 3. Yep. Then the output channel, define the number of output channel. The layer could also be called, it can be this, or can be this. The kernel size, it can be these values 3, 5, 7. Lower values learn smaller features, higher value learn larger features, something like that, right? It can be 2, but by default is 1. Padding, it can be one of these values, 0, 1, same valid. It can be any of these. So it can be 0 if you don't want to do padding to provide the input shape, or leave the target turns as if it is valid, or lowering the output. So we'll discuss this in detail in a way. Yep. Any question? All right. Any question? Okay. Now we have seen how we build our, architecture here. Everything here we build it. I will urge us, if I share this one in GitHub repository, please take a look at this one. All these layers I explained, the input layer, convolutional layer, you can see the padding, understanding all these hyperparameters, input size, padding, kernel size, right? All these are explained here. You can see them here. They are all explained, fully layers, flat layers. Oh, they have a video as well. So I think it would be good if you watch this one. I will share this one. It will be really nice for you to understand better, because we don't have time to go into the detailed nitty-gritty of everything. It will be really cool for us. So here we define the architecture. We don't have too much time, 3 minutes. We have remaining 3 minutes. But here, okay. So let me skip this one, I think. Here we are explaining all of these layers. Okay, so let me skip all this explanation. So what I'm doing, I will share this as well. Here is we are explaining, what is happening inside each layer. For example, the convolutional layer, what is happening inside the Maxwell 2D. Yeah, what is, but let me skip it. If we have time, we can go over. But we should know that they are just hyperparameter. So let's continue building our model. So since we have our architecture ready, which is this is our architecture that we can be used to train a model, which is this is the architecture. Let's go and continue building the model so that we can finish building this chapter today. Okay, let's set up our hyperparameter. So we need to set up optimizer, and we also need to set our loss function and gradient distance. So this we are using cross entropy loss because we are using multi-class classification. We have 10 classes, right? And also we have optimizer. We are using SGD optimizer, and we passing everything. So this is we are familiar with this step. Now we now have our architecture. We have our loss function, we have our optimizer. Then what next? It really allow us now to train our model, right? But remember, we already functionize our training step. We already functionize our test step, right? If we go back to yesterday, we showed this how we functionize this stuff. Yes, these are the code we talked yesterday. Training step, you model, data loader, loss function, optimizer, accuracy device. Now we do the trainings. So all this one is doing training. We already saw this one yesterday. And the training involve, you activate the training loop, you go into the batches, you do a forward, you calculate the accuracy and the loss accuracy, call the optimizers, call the loss backward function, and now call the optimizer to update the weight, do back propagation. So we have seen how we do training in PyTorch, which is basically 5 steps. Number 1 is do forward pass. Number 2, calculate the loss and accuracy after the forward pass. And now zero the gradient. That is step 3. Step 4, calculate the loss for the backward. Step 5, optimize the call back propagation to do to optimize. So this is the training step we already defined, and this is the test step we already defined as well. So if we want to do training, then what left for us is now, since we have our architecture, it's just to call this stuff to train. Yeah, so you can see here, we want to do training. How many epoch we want to train? 3 epoch. For epoch in TDQM, in the number of epoch, print the epoch. Now do the training. We call the training. So in the training, what do we have? Train data loader. What is our data loader? Train data loader. That is our data set. What kind of model do you want to train? Model 2, because here we create a model here, right? From our architecture we built, we create a model. Where the model? Yes, can we see that model 2 from the architecture we built, which is called Fashion Amnesty version 2? We create a model, which is our model. So this is the model 2. So we are working on it, right? So if we want to do train, we spare the model loss function. We are using cross entropy, which is the loss function. Optimizer, this is our optimizer. Accuracy, we are using accuracy function. We already know that. We already loaded. And device, we are using the device you have in your computer, which we set already. And the loss test step, we have you specify all this argument as well. And now here we set the timer. And now here we just start training the model. So here we can see I'm training because I made a mistake. I'm training on my computer CPU. I supposed to have trained it on GPU so that it will be faster. Look at how many minutes it takes, but or how many epochs? 2/3. So we have 3 epochs, but it's taking longer time. You can see 27 minutes it's taking. So that's why you see, like in deep learning, if you want to do deep learning, you need to go through, Colab. If you don't have GPU, I have GPU here, but I didn't activate it. I just running on my computer, and I'm also not running on my computer GPU because I'm using MacBook, and I have GPU base that run on PyTorch, but I haven't activated. So yeah, so that's how we can train the model. But I cannot move forward because the model is not finished, hasn't finished training. Now here, what I do is let's combine all the model, eval mode to evaluate the model, because we also have evaluate function we already created yesterday. Why the evaluate function? Remember, eval function. Yes, no, yeah, eval model. Yeah, this is the function called eval model, right? So this eval model also do evaluation. When you finish training model, then you evaluate the model, you evaluate your model on new test data set. So we have this function that we created yesterday, eval model, that basically you give you a data, and now it evaluate and return the model accuracy, the model loss and model accuracy, which we show yesterday. So here what you need to do is just to call that model here as well. That function, I mean. Yeah, so we can see that eval model, you pass which kind of model you want to work, and data loader, where the data is, the loss function that you want to do, and the loss accuracy, and now call it. This will, result in performance. Right. So I think, look at inside Laiko. What people do already. So I think that's what we have here. We can see if this model finish executing, we can see the performance will beat the performance of the model we have previously. Why? Because now we are using CNN architecture, and you can see now here we are trying to put all the models performance here. When this finish and return this guy, we'll see it shows the model with their respective performance, and we'll see that the model we trained last, which is model 2, is CNN architecture, has a better performance. So that's the main takeaway. Because today it's already, we have time. Time is against us, so we started late. We may not go into detail, but you can do evaluation as well in to find the best model, which we have here. And you can also plot confusion matrix. We already know confusion matrix, I guess, right? But you can try it as well. Okay, then finally you can set the best performing model. We already know how to, you can set model as well. PyTorch model, right? We know how to set the PyTorch model. Okay, so that's what we got here. It's now time for the prayer, but I'll share this one. You can run stuff until the end yourself. You'll be able to see, what we haven't finished. Yes. Any question? Oh, papa. Okay, so to recap, so the main essence of this chapter now, I think basically is to go through how we can train a deep learning model for image classification, which we inspire the chapter by going through mainly using feed-forward neural network. And we saw that yes, feed-forward neural network does perform well, but we have specialized deep learning architecture that can basically be used to give a better performance. So we said, okay, convolutional neural network, CNN, are the way to go. They are the best models to train image stuff. And now we introduce using how to be, CNN. We also said that the CNN basically has different kind of architecture. All you need is just to take already made architecture and build, work on it on your model. But also we have seen that deep neural architecture has many kind of hyperparameter, convolutional, hyperparameter, we have the padding kernel size stride, which we already discussed this one also. If for some of us that are attending House NLP, while I did a presentation on convolutional neural network, I explained all these hyperparameter stuff. Yeah,